Hello and welcome to today's research presentation. I am Muhammad Asiful Haq, lecturer of the Department of Electrical and Electronic Engineering here at the Green University of Bangladesh. Now, one of my research areas is actually on energy efficiency. But before I get into the research topic of today, let me give you a little bit of a background. Now, as we all know, that energy is actually one of the driving forces of the world today, and due to the growing population and the development that's been going on across the globe, the energy demand is continuously on the rise. The energy consumption is rising, and also the energy production from different types of fuel sources are also rising. Now, one of the key ingredients of the whole energy consumption mix, one of the most constant sources of load, is actually indoor lighting. Now, not just in residential areas, in the residential buildings, we can see that in some studies, 10 to 15% of energy consumption actually comes from lighting, which is significant. But when you consider the commercial buildings, some studies show that the lighting energy consumption can be as high as 40% of the total energy consumption. So that's a lot of energy that is being consumed in creating the artificial lighting environment. So any saving that we can do for in the lighting field can have a significant contribution in the whole global energy scenario. So that's why researchers are focusing on how we can make the lighting system more efficient. Now, one way to do that would be to use more efficient lamps. Now, we used to see incandescent, those yellow bulbs that we used to have in childhood. Those were pretty energy heavy. Now, compare that to the modern LEDs. For the same amount of lighting energy, the modern LED bulbs can be up to 77% more efficient. So that's quite a leap in that field of research. But another way to save energy from the lighting system would be to incorporate lighting control systems. Now, these control systems can be of different types. For instance, occupancy-based control, where the lighting can be automatically switched on or off based on the presence of the occupants of the room. The lighting can be scheduled to be turned on or off on a particular time of day. And what we're mostly interested on in this research is daylight linked lighting controls, where the artificial lamps can be switched or dimmed according to the available daylight outside. And some more complicated system can incorporate multiple times of control scenarios together. So these are the ways by which we can reduce energy consumption in the lighting system. Now, how much energy can we actually save by incorporating daylight utilization into our artificial lamp settings? Now, there are many existing methods that exist that can give us a prediction about how much energy can be saved. But obviously, when we studied these previous methods, when we did our literature review, we found that many of these methods actually have some drawbacks or shortcomings in their calculations. The first thing, the most significant drawback that we found is what we like to call light distribution. Now, imagine a workplace, maybe a private office or a open office plan. Now, there are a certain amount of lighting requirement that is set by lighting standards organizations across the globe that need to be met for a particular type of task. For instance, for office tasks, desk jobs, 400 lux is required to be kept at the work plane. Okay, so when we're designing a lighting system, that must be maintained. But what's often ignored is that in a whole work floor, not all of the space is actually the working plane. There are many spaces in the workspace where actually no critical task is being performed. People are just circulating around. So that difference between the work plane is actually not considered in many of the researches that we've seen before. Now, another factor that's not often considered when estimating energy savings that is possible from daylight is actually the variation of daylight. The available daylight in a particular office room can vary by a large amount throughout the working hours. Now, this variation of daylight needs to also be considered in any effective energy savings estimation program. So in our proposed method, we actually want to combine those two factors together to bring us to a new, more enhanced energy savings estimation. Now, in this method, we will be considering daylight utilization, but now, of course, we will consider the variation of available daylight. That's the first step. The second component would be to is what we are calling area segregation. It would be to separate the whole area of the floor into task area where we're performing the critical tasks, and the surrounding area where we're not performing any critical task, is just for use for circulation. So we can have two different lighting levels to get more savings from the room. So once we combine these two different components, we will get a more enhanced energy savings estimations. That is the proposal of our new method. Now, all the steps of this method actually consists of multiple mathematical equations that take raw or simulated data of the available daylight and artificial lamps. But for simplicity's sake, we can divide the whole set of equations into four steps. First of all, general dimming. This is where we dim the artificial lamp levels to the actual lighting that is required for that type of a room. This is without considering area segregation or without considering daylight availability at all. So after that, we consider the variation of daylight. We will take actual measures or simulated results of that particular office room and see how much available daylight is actually available throughout the working hours, and how much of that is high daylight, how much of that is medium, and how much of that is low. So we're considering daylight variation in the second step. And in the third step, we will calculate how much energy do we need from the artificial lamps to compensate the daylight in order to meet the required lighting level for a particular type of room. And in the final step, we'll do our energy calculations to come up with how much energy consumption is being made from a particular simulated or actual room. So for the simulation purpose, we have actually set up two different simulation cases. First of all is the test case, where we are developing a office space in a particular geographic location. But what's more important for us is the second case, which we're calling the comparative case. For the comparative case, we actually took a relevant research paper in this field published in a peer-reviewed journal earlier from a different set of authors. Now, we have replicated their exact same simulation scenario in our simulation platform, which is Dialux. Dialux is a professional lighting simulation software. Now, once we've replicated their scenario in our simulation software, now we can apply our method in their exact simulation room. So what can that give us? That can give us a solid comparison between the results that were published in their research using their previous method, and what are the results we're getting in the same room with the same simulation environments considered, like geographical location, installed lamps, and etc. And what are the results that we can get using our method, so we can get a very valid comparison between the two different methods. So what type of results do we get after applying our new method in the test case and also in the comparative case? So first of all, in terms of daylight availability, in both of our cases, we see that throughout most of the day of the working hours, we're getting a very high daylight level in both our test case and also the comparative case. Now, this can be different from different cases based on the geographic location, window size, and etc. But the interesting part comes when we do the energy calculations. In the energy calculations, we see that in the test case, without applying any of the steps of our proposed energy savings estimation method, the annual energy consumption of the test case simulation model is 843 kilowatt hours per year. But once we apply our energy savings calculations methods step by step, after the final step, we get down the energy consumption to 114 kilowatt hours per year. So that is an 83% reduction of energy consumption. But what's more important is the results from the comparative case. For the comparative case, when we did not apply any of the steps of the proposed method, the initial calculation was 534 kilowatt hours of energy consumption per year. Now, once we apply our method, each and every step, we get the energy consumption at 85 kilowatt hours per year. And that is a 73% reduction in energy consumption. So how does this compare to the original research that was published by the authors. So in the original paper, the authors reported that an energy savings estimation of 63% can be achieved using their method. Now, when we simulated their exact same simulation parameters in our simulation platform and applied our method to it, we got the savings estimation at 72%, which is 10% higher, which is quite significantly higher than the original research paper. So what are the key takeaways from this research? If you want to summarize, at the beginning, we have explored the importance of the lighting system in the overall energy consumption mix. So we've seen that lighting plays a significant role in the global energy consumption scenario. So in terms of saving from daylight, we have seen that many previous methods actually do exist, but we wanted to highlight on some of the shortcomings of the previous method to come up with a new proposed method that can give us an enhanced energy savings estimation. And when we applied that same method compared to a previous work, we get 10% more energy savings as compared to the original work, which is quite a significant increase. Now, this video is actually just a summary of our research work. If you want to read our full paper, it's actually published in the journal Symmetry from MDPI by a brilliant group of authors. Four of us are actually from the Department of EEE Green University of Bangladesh, with international contribution coming from Technical University of Denmark and also University of Technology Malaysia. So if you're interested in this field, go get the paper a read. I'll put the link of that paper in the description. It's an open access journal, so you can it's free to read the paper for anyone. So at the end, I'd like to thank you for being with us in this research presentation. In this channel, we'll be bringing you up-to-date research works from the Department of EEE, the faculty members of the Department of EEE. So stay tuned with our channel, and until the next video, stay safe and keep learning.